Hey there, and this is our introduction to numbering systems and conversions. This is the hardest unit in this class, but the good news is it only lasts a week, and it's important to know. The information is really important to know. The steps are really important to know if you're going to go into the computer's world. It's fun to know if you're not going to go into the computer's world, but it's more important if you're going to go in the computer's world. But the good news is if you don't understand it by Thursday or Friday of this week, then that's okay. You know, if you don't do as well in the quiz, you'll have plenty of opportunity. The other units are much easier and much more interesting, and you'll do a lot better. So it's one of those things we're only going to spend a week on, and this might be the only week you actually spend on it in your computer science career. It's one of those things important to know, but you're not going to use it all that much. So first of all, we go back to George Boole and Charles Sanders Peirce. Remember our unit on history, and Boole came up with a numbering system where he said, can you do math if you just have 2 digits? So in decimal, which is the numbering system we all use, we have 10 different numbers for representing any given amount of anything. So when we count, we really only have 10 ways of counting something. If we have nothing, we say 0. If we have one thing, we put a number 1 there. This number 1 right here, right? If we have 2, we use 2, and we use that all the way up to 9. But when we hit 9, we have a problem. When we hit the number 9, we have an issue. And our big issue is that we don't have a 10. We don't have any number, any symbol, any character for the number 10. We don't have that. So what do we do? Well, you all know what we do. You all learned how to count when you were 4 or 5 years old, maybe even 2 or 3. We put a 0 and we start back over at 1. And so 10 right here in decimal represents I have 1 10 and 0 ones. And then in 11, I have 1 10 and 1 1, and so on and so forth. And then when I get up to 19, then I have to add, and I go back to 0, but now I use a 2. And now I have 2 10s and 0 ones. So you guys know that. The thing about computers is some of the early computers actually tried to use the decimal system, and the hardware was clunky. It was very hard to program. So they said, what if we use light switches in a computer, and a light switch can either be on or off? And so we used Boole's system. It was Charles Sanders Peirce who came up with this idea of using Boole's system, where you only have an on or an off, or a 0 or a 1, and you can count that way. So we don't have a number 2. There isn't a third option for a light switch. It's either on or off. There isn't a third option for a transistor. It is either on or off. Unless you put a dimmer in there, but there's no hardware that can detect whether the light has been dimmed, right? Or whether the electrical current is strong or weak, right? So it's on or off. So when we have one switch, we can only count to 2 things. If we have nothing of that thing, so if I'm counting apples and I have no apples, I can flip the switch off. And if I have 1 apple, I can flip the switch on. But now we have a problem if I have 2 apples, don't we? I only have 1 switch. I've already represented 0 and I've represented 1, but now I need to represent that next apple. So I start back over at 0. And now I add a 1, but instead of counting 1 10, this one right here counts 1 2. So the second digit is counting the exponents of 2. In decimal, we add a digit on the decimals of 100. The exponents of 10. Let me say that again. In decimal, we add a digit every time we hit an exponent of 10. In binary, we add a digit every time we hit an exponent of 2. So we add the first digit at 2. We add the next digit at 4. So this here is counting 1 4. This down here is counting 1 8. That's a typo on my part. I'm going to fix it now. That's counting 1 8. This down here is counting 1 16. So I have 16 of something. If I have 16 apples, I use 1, and then I flip 1 switch on, and I flip the other 4 off. If I have 17, then I flip the first one on and the last one on and leave the middle ones off, and so on and so forth. So you have to ask yourself, how many things is each digit counting? Then in binary, things got really tricky, particularly in the early days of computer programming. Things got really tricky because the computer would say there's an error at 0. Well, if you have 300 switches and half of them are off, what 150, which of the 150 that are off is it going to be? If it says error at 1100, I mean, there's tons of 1100s, right? So in early computer programming, one of the first things they did was they said, we need to divide up binary numbers and use a different numbering system that will help us keep track of all these light switches, help us keep track of every bit. So they divided every set of transistors of 4 they divided them into 4s. And the 4s represent hexadecimal, or the exponents of 16. If you look at all the exponents of 10, they almost never, I mean, it's way out there before the exponents of 10 cross the exponents of 2. You have to fly way out there before the decimal numbering system gets to a binary number. And so it's way out there. But the hexadecimals intersect the decimals of 2 every 4 times. And so if you pull up a chart of binary of the exponents of 2 and the exponents of 16, you'll notice that every 4th one is the same number. You start with 1, but then 16 is the next one they share in common. 32 is the next one. That's 4 down. 16 is the next one. 256 is the next one. And then 4096 is the next one. So they learned that if they saved the transistors in bits of 4, those are called nibbles, and then every nibble, every 4 binary bits can be saved as a hexadecimal number. So right here, we have 1000. That can be saved as 8. Down here, we don't, on this chart, we don't get to 8, but we'd have to count all the way up to 256, but that's the next time they intersect. And so every 4 binary bits represents 1 hexadecimal number. And so in your computer, they're stored as binary, but they can be very easily translated to hexadecimal, which we're going to go over here pretty soon. And so the important thing to know is decimal is called decimal because you add a digit in the exponents of 10. So 10, 100, 1,000, 10,000, 100,000. Binary, you add a digit at the decimals of 2. So 1, 2, 4, 8, 16, 32, 64, and so on and so forth. Hexadecimal, you add on the exponents of 16. So notice here, I don't have to add a digit until I get to 16. Then I go back to 0 and 1. So 10 in hexadecimal is actually 16. Now, we still don't have characters to represent 10, 11, 12, 13, 14, and 15. So in hexadecimal, they use the first 6 letters of the English alphabet. So A is actually 10, B is actually 11, C is actually 12, D is actually 13, E is actually 14, F is actually 15. And so that's how they count. And so if I have 1A, that's actually 16 plus 10, which is 26. And 1B is 16 plus 11, which is actually 27, right? So that's a very tricky thing to understand. Consult this chart often this week and you'll do okay. So now let's talk about how do we convert between them. And let's talk about some terminology. Decimal is the numbering system using 10 digits, adds a digit every exponent of 10. I've already talked about this. Binary adds a digit every exponent of 2. Hexadecimal adds a digit every exponent of 16. And then substitutes the first 6 letters of the alphabet for 10 to 16. And then we have to understand this. When we get into converting, we need to understand that every single number, whether it's decimal, binary, hexadecimal, has a positional value and an actual value. The positional value is its digit place. And so if I have a 1, just a simple 1, the positional value of that 1 is 1, and the actual value of that 1 is 1. And you multiply the two together, 1 times 1 is 1. But if I have a 10, then the positional value of the 1 is actually 10, and the actual value is 1. So 10 times 1 is 1. If I have a 20, then the positional value of the 2 is still 10, but the actual value is 2, so we multiply 10 by 2 to get 20. We're going to go over that down below. You also need to know this. Superscript indicates an exponent. You guys knew that, but if you subscript a number, you're telling its numbering system. So 10 to the 16th, 16 is actually a 10 in hexadecimal's numbering system, which isn't a 10, it's actually 16 in decimal. And so so a subscript is what tells you if this is binary, decimal, or hexadecimal. So 10 to the, with a 10 subscript would be just 10, 10 to the 2 would be 2, and 10 down to the 16 would be 16. And so that's just a little bit of that. You guys have this document, you can look at it. So now let's talk about converting. How do we convert? It's easy to convert from binary to hex. I would encourage you, look at these worksheets. I'm going to go through them very quickly, but this just introduces you. But study these very carefully. The problems for your week are on these pages, but I also put them on the assignment. So you can do the assignment not on these pages. You can do them on paper and take a picture of the paper and upload that file, or you can just do a text entry. I do want to see your work, so make sure you do the problems. But up here, if I'm converting from binary and hex to decimal, it's actually pretty easy. This goes back to positional values and actual values. So first you want to determine the positional value of every digit, meaning how many things that digit is counting. Remember, the positional value of every digit is what is that digit counting? And you want to do that by writing the exponents above the digit. So you want to make a chart. This is the most helpful way to do this. I'm going to be looking for this chart. So the first thing you want to do is write the exponents of 2 on the top row. And so make a chart where you have the exponents of 2. Remember to start with 1 because 2 to the 0 power is 1. Any number to the 0 power is 1. And then 2 to the 1 is 2. 2 to the second power, 2 squared is 4. On 2 cubed is 8, so on and so forth. So just make that chart. Keep it handy. And then take your number, which is up here, and fill it in, right? Fill it in down here. Do you guys see that? So 0, 0, 1, 1, fill it in down here. And then you basically multiply everything across and add it, which we'll get to. If it's hexadecimal, make a chart of the exponents of 16. Remember to start with 1. So, because 16 to the 0 power is 1. So 1, 16, 256, 4096. And then fill in the numbers. So up here we had AA. But here we have 0, 0. So these are zeros, AA. So we only have 2 digits, so we don't need to worry about the 256, 4096. Then step 2 is, as I said, we just multiply the top row by the bottom row. So 1 times 0, 2 times 1, 4 times 0, 8 times 1, 16 times 0, 32 times 1, 128. The other obviously way to simplify this is just whatever's on up here, just add those numbers together. So really it's 128 plus 32 plus 8 plus 2, and we get 170. So in binary, whatever is on, whatever is a 1, add that number. If it's a 0, don't add that number. Hexadecimal works the same. So this was 16. The positional value of the second digit is 16. We're counting 16s. We're not counting by 10s. We're counting by 16s. And A is 10 in hexadecimal. And so it's 10 times 16. And then 1 times 10, or 10. And you see I did all the math down here. So you're just multiplying what's on top by what's on bottom and adding them together. So A times 1 plus A times 16, 10 times 1, 10 times 16, 170. Notice it's the exact same number as it is. So that's the easy part. You just make a nice chart. You put the exponents on the top starting with 1, and then you fill in the number on the bottom, and then you multiply and add, and there you go. So once again, come back to this and read it. There's problems there for you to work on. Should be pretty easy for you. And so now is where things get tricky. Now we have to convert from hexadecimal to decimal. This is where things get really hard, so try to follow along. You can look at other internet tutorials and try to figure it out. But basically, you need to begin with comparing your decimal number. In this case, our decimal number is 63,232. You need to begin by comparing that to your hexadecimal exponent chart. So the good news is we never get bigger than a 4 hexadecimal digit number. And this actually 63,232 falls right below the maximum we have. And so so you just look at the chart and you know that 16 to the third is 4,096. So you know we have 4 digits. I think 16 to the fourth is like 64,000 something. So we know we know we only need 4 digits because 16 to the third. Remember, we're counting 0. So 16 to 0 is 1. 16 squared is 16 to the 1 is 16. 16 squared is 256. Cubed is 4,096. So we have 4 digits. If I'm doing this by hand, it's helpful to make 4 blanks right there and just draw 4 blank lines that you're going to fill in. So draw 4 blank lines. So then we have to divide our number, so 63,000, divide it by the integer, by the decimal counterpart. So we have to divide 63,000 by 4,096. We get 15 and change. So we know our first digit is 15. So up here, I'm going to draw my 4 blanks again. We can erase this one and write an F because in hexadecimal, 15 is an F. So we write an F there. Then we basically have to multiply and subtract. So we multiply 4,096 by 15, and we get 61,440. So then we subtract that from our original number, and we know that we have not yet counted 1,792 of whatever we're counting, whatever number we're saving. We have accounted for 61,000 of them. But now we need to figure out how to account for the remaining 1792. So we basically just start over. So now we know that 16 squared is 256. Found another typo. So we divide 1792 by 256 equals 7. So digit number 2 up here is a 7. Right? We know what digit 2 is, and then we subtract again. 256 times 7. 1792, and look at that, it comes out even, so we know the remainder 2 digits are actually zeros. Anytime it comes out even with no remainder, like we have a remainder right there, then we know that that digit is a 0. So it's F700, which you see down here. So it's tricky. Read this again. Hexadecimal is the hardest one. But it's consulting your the 16 exponent chart, figuring out which one is the closest without going over, dividing, and then erasing, forgetting about the remainder, and multiplying and subtracting to figure out what the remainder actually is, and then filling in your chart as you go. There's some problems for you to work on. Binary, it's a little bit easier. But it's the same logic. So determine which 2 exponent is up to the number without going over. So if I have the same number as above, 63,232, the next one that's closest is 32,768 actually, and that is 2 to the 15th. So that means we're counting 16 digits. So once again, super helpful. And to draw 4 of these, it's really helpful to divide them up into what's called words, or nibbles, sorry. So, and that was underlined, my underline was turned on there. So, really helpful, divide them up into 4s just for keeping everything good. And then we divide the number by its decimal counterpart, and then we subtract the next one. We still multiply, subtract, but we don't have to do any subtraction. We could just keep going. You just go down. So you always know the first digit is going to be a 1, by the way, in decimal. And then you just go all the way down. The math's all down here, and on it goes. So you just find the nearest ones and just keep going down. So it's a little bit easier with binary. You don't have to subtract. And then the really easy one is, how do we convert binary to hexadecimal? Well, remember that every 4 binary bits is 1 hexadecimal number. Let me say that again. Every 4 binary bits is 1 hexadecimal number. So divide it up into nibbles, because every nibble, every 4 bits is 1 number. and then figure out the value of each nibble. So here I have 0000, so that's going to be a hexadecimal 0 because there's nothing there. And then you basically make the same chart you had way back at the first one. When we get out to here, we treat each nibble as its own number. So each nibble is 1248. 1248. So here we have 1 plus 2 plus 4. So 4 plus 2 is 6. So that's 7 in binary. So our next hexadecimal number is 7. And then here we have 15, which is the highest you can count with 4 bits without having to add another one. And they're all on. So we know it's a 15. 1 plus 2 plus 4 plus 8 equals 15. So our hexadecimal number is F700 because 15 is F in hexadecimal. Pretty easy to do. There, you just treat each nibble as its own number. So this is just 1248, 1248, 1248, and then you add them up, add up the ones that are on, and there is your hexadecimal number. So I know I went through that really quickly. If you're in class, we'll do it slower. But the good news is, for those of you online, you can subtract, you can rewind, you can hear what I said again, and you have these available to you. There's also some really good sources online that you can find. There are converters online, but remember, I still want to see your work. So don't use the converters. I want to see your work. If you just give me the answer, I'm not giving you any points. So make sure you show me your work. So good luck. Let me know if you have any questions, and I'll try to explain it better. I also can set up a Zoom meeting for you if need be. Good luck out there.